Hello everyone, I'm Kyoung-Hee Kim, a professor of architecture at UNC Charlotte. Today I'll be discussing drought resilience in the built environment. As we discussed in the heat resilient design video, global warming contributes to more frequent and intense hot days, which increase the likelihood and severity of droughts and water shortages across the globe. This slide shows the global population at risk of water stress, comparing projections between 2019 and 2050. Water stress is determined based on water availability, with extremely high risk, indicating regions where more than 80% of available water is already depleted. In 2019, an estimated 2.2 billion individuals faced severe water stress. This number is expected to rise to 2.8 billion by 2050. Other water stress categories show upward trends which indicate a greater demand for limited freshwater resources. Rapid urbanization and high population density are expanding the prevalence of water-stressed regions. Water scarcity and prolonged droughts negatively affect crop yields, local economies, and the health of natural environments. Globally, the frequency and intensity of drought events are increasing. Preventive policies and strategic planning are necessary to manage limited water supplies and to develop city settings capable of conserving water and improving water shortages. Let's review the resilient design framework consisting of original state, mitigate, adapt, and recover. In the original state phase, water systems and infrastructure fully operate under normal conditions with the ability to function during drought conditions. The mitigate phase involves proactive steps to reduce water demand from the outset and limit the drought's impact. When water becomes scarce, the water system enters an adapt phase during which operations enable water reuse and adjust to alternative water sources such as on-site treated wastewater supply. Finally, as rain returns, the recover phase allows the system to bounce back toward its original function. This slide shows a breakdown of water end users for a typical office building. It is essential to reduce water consumption at the outset, and understanding the pie chart is important. The highest water end user is domestic and restroom use, followed by cooling and heating operations. Landscape irrigation is also major water use, along with kitchen and dishwasher activities. Another comparison can be made in water consumption across all large commercial buildings, office buildings, and inpatient healthcare facilities. Healthcare facilities consume water predominantly due to their specialized and essential operations. The colors in the bar graphs represent the years of construction. While recent healthcare facilities have achieved enhanced water savings, offices and other commercial buildings show little to no improvement in water conservation. This slide shows an outdoor view of Google's Bayview campus in Mountain View, California, a notable example of drought-resilient design. As shown in the figure, the campus features large wavy roof structures for rainwater collection, along with water ponds on site. Google designed this campus to be water positive by 2030, meaning it will put more water back into the local environment than it draws from the municipal water supply. This slide shows a building section view with drought-resilient, water-positive design. The campus uses all the resilient design strategies, mitigate, adapt, and recover, that we discussed previously. At the building level, the campus minimizes water consumption by integrating ultra-efficient fixtures, drought-tolerant landscaping, and cooling systems with lower evaporation rates. The campus integrates closed-loop water systems to reuse reclaimed water. It operates an on-site wastewater treatment plant designed to handle domestic blackwater and greywater originating from lavatories and kitchens. The wastewater is cleaned via multi-stage treatment to achieve a quality suitable for reuse in non-potable applications such as landscape irrigation and toilet flushing. Ultimately, the drought-resilient design integrates the building geometry, the site, and the water systems to function holistically for rainwater harvesting. When it rains, water is funneled from the sloped roofs and pervious pavements into on-site ponds and water storage across the campus. Those ponds on the site are also part of an extensive rainwater capture system. According to Google's estimates, the Bayview campus conserves over 1 million gallons of potable water each year compared to typical office buildings. Here we have the Kendeda Building for Innovative Sustainable Design at Georgia Tech, a university building that achieves net positive water use. In the photo on the slide, you can see Kendeda's distinctive roof, a broad overhanging canopy integrated with solar panels. This slide illustrates a building section with a closed-loop water system. This is part of the building's pursuit of the Living Building Challenge's water petal, which requires a project to supply all its own water and manage all wastewater on site. Kendeda doesn't have a traditional sewer connection. Instead, it uses composting toilets that treat waste on site with no water use. Greywater from sinks and showers is cleaned through a constructed wetland and then returned to the soil via infiltration gardens, recharging the groundwater rather than draining away. The roof geometry is configured to maximize rainwater harvesting, supplying all Kendeda's domestic water needs from captured rainwater on site. The rain from the roof is directed into an underground 50,000-gallon storage tank. Water is then filtered and treated to become potable water. Potable water means that it meets code requirements for drinking, lavatory faucets, and shower systems. Ultimately, Kendeda returns more water to the environment than it uses. This positive water balance contributes to regional drought resilience while minimizing reliance on municipal water systems. This video was supported by UNC Charlotte in collaboration with the US ASEAN Smart Cities Partnership. For further inquiries, please contact Kyoung-Hee Kim at UNC Charlotte